Hello, everyone. My name is Miguel Blanco, and I am a mechanical engineering student at the University of Houston in Texas. As a part of the Robotics Institute Summer Scholars Program, I've had the privilege to work in the Foam Robotics Lab alongside PhD student Dominic Bauer and Dr. Nancy Pollard. Throughout this summer, I have developed a benchmark test on the endurance of 3D printed submaterial robot fingers. So, first and foremost, why are soft robotics hands important? Well, they're currently offering great promises in a lot of different fields. Some of the current industries in which they're thriving are prosthetics, since their increased degrees of freedom, flexibility, and dexterity enables for more freedom and control for users. In personal robotics, their softness, durability, and malleability allow for safer and more personalized devices for people in need. And in manufacturing, this same softness and dexterity allows companies to handle more fragile materials than their standard rigid manufacturer normally wouldn't be able to manage. So despite all of these benefits, what is the current problem with this technology? Well, it is because it is a very recent breakthrough, and most scientists don't fully understand the capabilities and limitations of these technologies. Because of this, we want to better characterize them. We're testing for their repeatability, endurance, and speed to improve designs and understand our present state with soft robotic hands. So, what will be the proposed framework? We will conduct an endurance test, continuously curling the finger upon itself until complete failure. For this purpose, we have developed a test bench in which a dynamixel motor, a very standard servo motor using soft robotic hands, will be attached through a nylon tendon to a 3D printed soft finger. Uh, it has been created through Ninjatek Ninja Flex filament, and we'll be using different variations of this material through the experiments. Then, to record all this process, we'll be using an Interreal Sense D43.5 camera. And as you can see in the next here, we'll be taking a picture during each release and pull positions. This is because these are the most fundamental stages of the experiment that we want to analyze, since they represent the full extension and grasping of the hand. As you can notice here, there are going to be different color dots alongside the finger. This is because the soft robotics hand previously created a software able to track the trajectory of different images of soft robotic fingers. In order to have a better understanding of our experiment, here's a picture of what we're going to conduct. Each time the finger reaches a pull position and release position, the camera will take a picture, and then that picture will be processed through our software. Once that picture is processed, we'll obtain the following information. First, we will have a digital skeleton of the finger in order to properly track its trajectory. Then, after those processed images, we will have the different iterations and deformations of the fingers throughout this process. As you can see in this example, the finger achieved more than 30,000 iterations, and you can see its different changes. Now, as for the results, you can see here the distance and standard deviation that was obtained through this software. For the distance, we obtained the maximum distance between the end effectors and the distance between the end effectors' initial and final positions. The most important value in this chart is the distance between the end effector's initial and final position. This is because this value represents the consistency of the finger. The greater the distance is between the final and initial, the more deformation the finger was subjected to, meaning it is a less reliable finger. The only exception in this chart, however, is the reinforced Ninja Flex design. Since as you will see in the next slide, it achieved more than 29,000 iterations, clearly outperforming any other of the designs. As for the standard deviation, we obtain, of course, the deviation in the x and y coordinates. We really care about the x coordinate specifically, since it represents the full flexing of the finger. If the if the finger is not able to completely perform this motion throughout the entire experiment, it's not as reliable as we want it to be, since one of the most fundamental characteristics that a finger needs to have, a soft robotic finger needs to have, is complete grasping. Now, in this next stage for results, you can see here the different versions of the fingers, as well as the average and standard deviations for all the values and processes. For the normal cycles, as previously stated, the reinforced clearly outperform any of the other ones. Well, this is because one of the main defects of our finger design was that as we continuously went through the process, the tendon ripped through the material, and eventually like caused several damage that ended up in full-on breakdown. However, the silicone reinforcement that we installed prevented or at least diminishes as much as possible this damage. These also cause an increased current, as you can see in the max release and max current values, max pull current values. This is because as more surface area that the tendon had to endure, the more current that the motor had to exert in order to completely curl the finger. For all the values, such as the max release velocity and max pull velocity, they're very similar through the different iterations because we use the same motor throughout the entire experiment, as well as only changing the width, but not the length of the finger. In that way, not actually the torque that was exerted by the finger. So as a conclusion that we reach from all this data is that the softness of Ninjaflex and 83A and 85A causes notable damage after 5,000 iterations. As well as that silicone reinforcement significantly increased durability up to at least 30,000 iterations before breakdown. We still need to test further for the reinforcement designs and other versions to see how much we can increase the durability and lifetime of these fingers. Also, we discovered that the optimal finger joint radius is of 2 millimeter with a gradient of 40 degrees and a 19.3 millimeter width. And we did previously try different variations with this design, such as a 3 millimeter and 1 millimeter joint radius, a greater gradient, and other widths. However, because these values didn't reach even a substantial amount of cycles in order to be considered as data, they didn't provide us with valuable understanding of the material. Therefore, they were discarded. Now, it didn't, as previously stated, Ninjaflex 85A and its reforms design demonstrated the most consistent motion, and that 85A and 83A Edge have a similar endurance, current, and velocity. So for future work, we could explore different finger designs with distinct tendon quality and placement. One of the main things that we overlooked and later we noticed was that our finger just had a curve in which the tendon hole went through. However, different variations of this hole could be made in order to make the finger more efficient, as well as placing more tendons in different places in order to see how that would affect the finger motion of the finger. We can also compare different soft material for the finger, analyze the effect having its properties. The Ninjaflex is only one of the many that are available in the market, and it will be very insightful to discover all the different properties and endurance of all these materials. And of course, compare the performance of different actuators to the dynamic motor. The dynamic motor is a standardized motor, but it isn't the only one in the market. So we could see the different variations and different values that all these motors give, as well as maybe even independent new motors that could be made specifically for soft robotic hands, and see how they compare to all these different processes. Well, that is the end of my project and presentation. Thank you very much for watching, and I hope you have a good day.